sounds like a serious problem, but as the gentleman said, if delta x and delta t are small enough, then this spurious reflection decreases. So the spurious reflection we avoid it by So if you use sufficiently small delta x and delta t, then this can be avoided because if delta x, k delta x, and k delta t are much smaller than 1, then from this equation 1, unfortunately, it is behind the board.
You mean 2.x and...
Yeah,
only
delta t. Thank you. So if this condition is satisfied, then we can use this Taylor series expansion for these two cosines appearing in equation 1. Then what you get is omega delta t square is approximately equal to So if delta x and delta t are quite small, then you recover the physical dispersion relationship. For physical dispersion relationship, you have constant phase velocity c. So your spurious reflection decreases. But what is exactly small enough delta x and delta t? So when you say that k delta x is sufficiently smaller than 1, that means delta x is sufficiently smaller than 1 over k. This is lambda over 2 pi. This is approximately lambda over 6. And when you say that something is much smaller than lambda over 6, you say that delta x is smaller than 1/10 of lambda over 6, right? Which is lambda over 60. This is actually extremely small delta x. So you have to put 60 grid cells within a single wavelength. That's a lot actually, especially in 3D. So this is computationally very expensive. So we just use delta x around lambda over 20, and what's that minor problems. Okay, so if lambda, delta x is around lambda over 20, then stress reflection is not that large, so you can live with that. So lambda over 20 is kind of trade-off between accurate simulation and performance. Okay. So, continuing the dispersion issue, I'll talk about dispersive media. Was there any question until now? Yes.
What about 3D case? How dispersion look like?
For what?
For 3D case.
3 delta K?
3D case.
3D cases.
Yeah.
The dispersion relationship. Actually, there was a question earlier. So there was a numerical dispersion, right? Dispersion relationship. You can just add the same terms for delta y and delta z. So the 1 minus cosine omega delta t is equal to 3 terms. The sum of the three terms. Oh, actually, I forgot to mention one thing. I'll write the dispersion relation again. Make sure. So this was question 1. So a few people asked why we choose the c delta t over delta x close to 1, right? If c delta t over delta x is equal to 1, then you have 1 minus cosine omega over t equals 1 minus cosine a delta x. So you have omega is equal to delta s over delta t, k, which is ck. So again, you recover the physical dispersion relation. This actually holds only for 1D. So delta t equals delta s over c is called magic time step. So if you choose, so you can choose any delta t that makes c delta t over delta s less than 1 to make the algorithm stable. But if you make the quantity, the ratio exactly 1, then you do not suffer from dispersion, numerical dispersion issue at all, only for 1D. The reason it doesn't hold for other higher dimensions is that you don't have this simple relationship. You have extra terms, so even if you satisfy this kind of relationship, I mean, even if you choose the so-called magic time step, you do not recover the physical dispersion relationship. So only for 1D. Yes.
So, if the time step covers the whole simulation region, how would a program like numerical engineer it for a non-uniform grid to keep a constant ratio?
They just make delta t small enough.
Okay, so it's not 0.99 everywhere. It's 0.99 at one point, and then it's just.
That you mean that thing? Yeah. So you choose. For non-uniform grid. Actually, that is very good question. You choose so you have to satisfy this relationship. So c delta t over minimum delta x should be less than 1, because then for the maximum delta x, you still satisfy this delta t condition. But that means for inside coarse grid, you suffer more from the numerical dispersion issue.
So you should be careful how small you make your small circle.
Yeah. Yeah, you cannot make the smallest squid arbitrarily small.
Will someone use a non-uniform time step?
No. Update equation updates the whole field in the system at the same time. So you cannot assign different delta t at different positions.
But what about like uniform over the grid points, but over the course of the simulation, like, you know, if you know that your plane wave is going to be interacting with your scatter at the beginning, but then after there's some longer propagation that you don't need as fine resolution for.
Maybe that's doable. Yeah, I think that's a good idea. I'm not sure if somebody implemented that already.
Generally, you put a coarse grid in that region anyway. It's just that if you make your resolution too fine, your scatter region, coarse grid where it doesn't matter might be a little less accurate, but you said it doesn't really matter.
So I think what you mean is, for example,
the question was just like, how does this translate if you're talking about time instead of space? And so, like, you could have whatever spatial grid that you want. The question is, can you have non-uniform time steps over the course of your simulation?
So what I'm saying is that, yes.
Well, the fact that you chose C delta t over delta x to be close to 0.99 already means that if you fix your spatial grid to be the same, if you increase your time step, you're going to reach numerical instability, right?
Oh yeah, and then the regions where you have near zero field are going to start like shooting up quite
But if you decrease delta t, not increase delta t, if you only decrease, then I mean, as long as this condition is satisfied, you can reduce delta t, I think, during the simulation. Yeah. So for example, but I'm not sure if that solves the numerical dispersion issue. So you have to decrease both delta t and delta x small enough. So just making delta t small enough does not solve the numerical dispersion. So
At no point could you make delta t bigger than visibility, even if you're
Right, I mean, that's the same for spatial.
but the key point is that you have to use the same delta t all over the space.
Are these issues identical in FDTD, or is there,
In
are they
FDTD,
different enough that it's...
In FDTD, there is no delta t. So you don't have numerical dispersion issue. But yeah, frankly, people do not use FDTD a lot. So there's no numerical dispersion study for FDTD done rigorously. So yeah.
I guess certainly along the question for his lines, if you know that your field is active in regions where you don't care about, could you implement some sort of energy conservation so that if you were to go past the stability limit in a region where there isn't a lot of field, it would just make sure that you don't get field that shouldn't exist, but you're still stable where the field does matter?
I think that's one way to handle this issue. But people usually want the algorithm want to keep algorithm simple, right? So yeah, but even though FDTD has been used for a very long time, there's still room for improvement. So if you guys are interested, then you can take 2 philosophy physics to be taught by John Fan, Professor John Fan, and write a paper about FDTD. So last time we considered the vacuum case. So but for more general cases, so we use B field instead of E field, and here the D field is the response of the material to applied E field, right? So D is response to E. And the properties of the response let's say if you put E1 and get D1, and E2 and get D2, then if you put E1 plus D2 and E2, then you get E1 plus D2. And the second property is that if you put ET and get ET, and if you put ET minus T0, then you get ET minus T. Right? So if the medium is linear, then if you know the results for the separate E fields, then you know the results for the sum of the E field. And because the system is shifting time invariant, if you delay the E field input signal, then you also get the delayed E field output signal. And so this system is actually linear shift invariant system, and for any linear shift invariant system, this is called LSI system. The input and output are related by convolution. So your dt is obtained by ET through some convolution relationship. So here, epsilon t is impulse response. Right? And the causality condition is if this system is causal system, then your impulse response should be 0 whenever the time is less than 0. So your dt is then your limit of integral changes from infinity to t. So why this means a causal system? So let's look at this first case, right? The original definition. Then if epsilon t is not 0 for t less than 0, then here for tau less than 0, you still don't have, here for tau greater than t, your epsilon is still non-zero, right? So we are evaluating E at t, but E field in the future affects the D field now, so that violates causality condition. So to keep it causal, you have to satisfy this causality condition for the impulse response. That's the relationship between E and E. And let's look at the update equation for sparse media. The last lecture, we had this.